Right, so we are going to learn the chain rule. And what the chain rule is looking at is when you have a function inside of another function. So in our function notation, this can be shown in two ways. You're probably most familiar with this way, because you can really see that the function g of x is inside of the function f. I think that notation is easier to see that, but this means the same as this. Right, that little open circle means that f is a function. F of g of x means g is inside of the function f. So if we had a function that's listed here, and I move these away here, if you have x plus 2 cubed, then you have x plus 2 as the function inside of x cubed. And what Joseph said before is, can I just bring that number out in front? Well, we saw it in the last example that it didn't quite work, but let's see what happens in this example. Right now, the only thing you would know how to do is expand it. So if we expanded it completely, and here I used Pascal's triangle and the binomial theorem to expand it, and you combine your like terms and simplify things, you get x cubed plus 6x squared plus 12x plus 8. And then the derivative becomes 3x squared plus 12x plus 12. And if you factor that, ooh, this one did work exactly the same as what we wrote in green before. Don't think this one is in your notes, but if we tried 2x plus 1 cubed, and you don't need to write this down, you can just watch. What would you have to do? You'd have to expand it completely. There's Pascal's triangle, 1, 3, 3, 1. And expanding each part, remember the first one has cubed, then squared, then 1, then none of them. And the second term, there's one of them, then none of them, then 1 squared, then 1 cubed. And you expand this completely, and you get this function, which is easy to take the derivative of. And then if you factored this, took out the 6, and factored that, you get 6 times 2x plus 1 squared, which seems to go against what happened last time. Last time we just brought the 3 out in front, but now we have a 6 there. But if we took that 6 and said, I want a 3 out in front, then I have an extra 2 that needs to be afterwards or multiplied by that to get the 6. Where does that 2 come from? The derivative of the inside is 2. Does that fit with why nothing changed the last time? What's the derivative of the inside here? 1. So I guess if we technically put times 1 there, that doesn't change anything. So it seems to fit with a pattern. So now here, we're going to pretend that we had all the time in the world. We expanded each of these, including 3x squared minus 7 to the 40. Expanded it completely, got all 41 terms, took the derivative of those 41 terms, leaving us with probably 40 terms, and then had the ability to notice that, oh, that's just 3x squared minus 7 to the 39. And factored it, and after factoring it, notice the following. How does your pattern looking? Is it looking like we're doing our power rule first? The number coming in front, subtract 1 from the exponent. Number coming out in front, subtract 1 from the exponent. It seems to be happening. What about this part? Is that fitting the pattern that you saw? Where does this come from that we multiply afterwards? Does that come from the derivative of the inside function? Yes. Fascinating. So instead of having to expand these, especially that 1 to the power 40, and then simplify and take the derivative, now we can do the derivative of the outside function and then multiply by the derivative of the inside function. And sometimes you'll have a function inside of a function inside of a function. Then you would do the derivative of the outside function, derivative of the inside function, which would have a inside function inside of it as well. So we'll look at all of that. But that is the idea of the chain rule. Okay? We're going to highlight things so that we can see things better here. Okay? We have y is a function of u, and u is a function of x. So x, okay, so u is inside of y. And here we have f of x is inside of g of x. So this first derivative is the derivative of our outside function, and then we multiply by the derivative of our inside function. So we're going to see this when we do more examples, it'll become clear. But the most common outside function is a power function to the power of 3, or the exponent is 7. As is this case. The inside function is 3x plus 6. The outside function is the power of 5. Now, we can, if we want to, and I'm going to say over time we're not going to do this, but to start, we can label our functions. We can say that our inside function is u.
We are going to finish up with the last group of grade 10 boys that did not get a chance to do Seeing Teens last week.
So if we label our inside function with u, 3x plus 6, and we then say what is our outside function going to be, our outside function is y equals u to the 5. Then if we just take dy du, okay, it says, our formula says dy dx will be dy du times by du dx. Well, when we take the derivative of u to the 5, it just becomes 5u to the 4. When we took the derivative of u du dx, we just got 3. And we get our final answer as 3x plus 6 to the 4 times 3. I'm going to say that eventually you're going to be able to go to this directly. You're going to be able to say, what's my outside function? My outside function is my power. So the 5 comes out in front, subtract 1 from the exponent. And the key thing here is you take one little step at a time. You don't over-derive. Take one little derivative at a time. So if I'm taking the 5 out in front and subtracting 1 from the exponent, this part doesn't change. Then I look at my inside function and say, can I take a derivative of that inside? Yes, it's 3. And then you'll multiply by 3. Okay? So here's the overall idea that comes. This method isn't the greatest to substitute. We're going to do it directly. So what does directly look like? We'll just write this out. What's our outside function? So I sort of put my hands out like this, and I just sort of start bringing them in and see what do I hit first. And I hit that exponent of 6. And I say to myself, well, how have I done derivatives in the past when I have an exponent of 6? Well, the 6 would come out in front. And if that 6 comes out in front, hits that 4, you see you'd get 24, right? Do nothing to the inside because you're doing that first derivative, which is an exponent. 6 comes out in front, subtract 1 from the exponent. Now that I've dealt with that law, I look inside of it. What's the function that I have inside? 5x cubed plus 2. Can I take the derivative of that? Yes. Okay? It's just 15x squared. Now, I don't take the derivative of my derivative and keep going there because I already looked inside. And when you look inside of the function, the 5x cubed plus 2, could you do that derivative all at once? Yes. So then you're done. Whereas this one, originally, you couldn't do the derivative all at once because there's still a function inside of the function. And then if you wanted, you could simplify this. Most times we'll be allowed to leave it exactly like this. One of the strategies that we're going to use a fair bit for this is we're going to change our exponents. If they're positive exponents, we can move that up to the top and make it a negative exponent, which will allow us to do things faster. This could be done as a quotient rule with a chain rule, okay? But it's going to be easier if we do it just as a chain rule. But I'll show you what it looks like as a quotient rule and a chain rule right after. So we're finding the gradient function. That's just another word for the derivative because the derivative is a function of all the slopes. So the word gradient function means the same thing as the derivative. And once we've changed it to that -4, that -4 comes out in front. I wrote it as -4 times 3. You could have written -12 right away. That would be fine. We leave the x squared plus x and subtract 1 from the exponent. It's going to be tempting to write -3 because that seems like 1 less. Be careful with the negatives. And then the derivative of the inside is 2x plus 1. So if you wanted, you could write this now with that x to the -5 back on the bottom. And this would be the answer. Just for fun, let's say we don't think about moving that x squared plus x to the top, and we think of this as a quotient and a quotient rule, because we have a function on the top and a function on the bottom. So what does that look like? How do I do the derivative of the quotient rule? The first thing was you keep the bottom the same. Okay. So far, so good. No problems. Then you multiply by the derivative of the top. What is the derivative of the top? The derivative of the top is just 0 because it's a constant. Then you would subtract. Now we keep the top the same. What's the derivative of the bottom? Well, the derivative of the bottom is a chain rule. So with the chain rule, you'd bring the 4 out in front, subtract 1 from the exponent, and then multiply by the derivative of the inside. All over, quotient rule says take whatever you have on the bottom was x squared plus x to the 4 and square it, which will give us x squared plus x to the 8. Now I'm going to argue that these two answers are the same. I mean, if you saw them on the streets, you'd probably think they're twins, right? They look so similar. No. Right now, they look really quite different. But if we look at what's there, this is going to be 0, so this is going to go away. Can you see that you have negative 3 times 4? That'll give me negative 12 on the top. And can you see that this x squared plus x to the 3 will cancel out with 3 of these, leaving x squared plus x to the 5 on the bottom. Then once that's canceled out, I still have a 2x plus 1 on top, and yes, they are identical. However, in this case, can you see that taking that extra step at the beginning and changing this to an x squared plus x to the negative 4 allows you to do the chain rule immediately, whereas if you use the quotient rule, you still had to do the chain rule inside of it, plus you had to remember all of the extra stuff that the quotient rule has. So in this case, taking that extra step at the beginning, if you can see something at the beginning that's going to make your derivative easier, it's a good algebraic thing to do. So here we have a 5th root. So the first thing we're going to do is change that to the power of 1/5. Then we're going to look from our outside in, see which function we hit first. Try this on your own. I'll put the answer up in a second. Bring that 1/5 in front, subtract 1 from the exponent, negative 4/5. So you're going to get really good at subtracting 1 with fractions, I said earlier in this year. And this is one of the reasons. And then the derivative of the inside is going to be 6x plus 7. If you wanted to write it with radicals in the end, that negative 4/5 would move to the bottom of your fraction. Then the 5th becomes a 5th root. So this could be written this way. But it would be fine to leave it as we see here in the final line in green.